All right, please take it from here.
Thank you, Hatim. Good afternoon, everybody. Thank you very much for this wonderful arrangement. This is fun. And I've been following Hatim on Twitter, and he posts, and I'm like laughing when he posts pictures of mass group meeting. So this is an excellent idea, and thank you for having me in your weekly group meetup. I hope all of you and your families are doing fine wherever they are.
Thank you.
And I see a number of familiar faces, so this is really wonderful. David, hello.
Hi, Chandra.
Bob, hello. And see, Saber is trying to connect, I think. Bilal, hi. A lot of Twitter followers here.
We brought Twitter, yes, exactly.
Well, how did you get to New Zealand?
I need to change the background. We did like a online virtual meeting for a group meeting. So,
Right.
Okay, so yeah, I think I will unmask in a little bit, but me trying to move the mouse here. Okay, can you all see my screen?
Yes. Yes.
Okay, wonderful. So today we will look into some of the high performance computing, programming models, machine learning, related research in a lab called Computational Research Programming Lab somewhere in the Northern Hemisphere. We will find out soon where. So I have a few topics, and you see some beautiful pictures of maybe a university, maybe a national lab, maybe an institute, maybe an industry, you never know. But the pictures are kind of evident, so I'll let you guess. And thank you to all the collaborators. So that's a must. I didn't want to mask that part. So thanks to all the funded organizations without which none of these work will exist. And I will give credits to my group as well, a little bit towards the end. So the suspense remains for a little bit longer. That's why I can keep the mask on. Okay, so that's the outline, basically, and we don't have to do it all. I know that you all have to get on with your group meeting. So I wanted to start off with the data analytics and machine learning because it's a relatively new project and I didn't want to run out of time towards the end. So I'll kick off with that and some case studies based off of programming models, abstractions, algorithms, and some performance, analysis. I have 3 of them. I do want to talk about one of them for sure. And we can do the other 2. We can take a poll based on, what your interests are. The 3 case studies are plasma physics, biophysics, solar physics. So I do want to tell you about plasma physics because it's a massive project. Between biophysics and solar physics, feel free to send me a chat or, just do a poll or whatever we want to hear about. Both of them are wonderful projects, and for one I have results, for one it is cooking, it's still baking. So I can tell you what does not work and what we should avoid to do. And performance benchmarking, I do want to talk about that because I know you folks have this awesome supercomputer there. So, at some point you want to probably use a work in progress benchmark suite to stress test hardware, software tools. And I want to tell you what we are building as part of a spec HPG organization so that, when we release it, you guys might want to use that as part of your, performance testing, if you like, for your systems. So I wanted to let you know about that. And then preparing compilers for scientific developers. It's a test suite project. Again, it's a massive project with respect to testing compilers and eventually the training and education out there. Okay, maybe I can remove the mask because I want to have my tea. All right, hello everybody. Wonderful to see you all. So now that I've removed my mask, so I'm Sunita Chandrasekaran from University of Delaware.
You look like a nurse, Sunita.
Tell me again.
You looked like a nurse at some point.
I do want to say, I hope I'm not offending anybody with my scarf. I did look up YouTube videos to make sure I got it somehow right.
You're just fine.
So I'm at a university here, and I meet, I think, several of you in conferences and stuff, and I'm glad we're doing this. So it's very good to see you all. Maybe we won't meet each other in this year, but it's very good to see you all virtually. So thank you for taking the time. Okay, so feel free to ask any questions you have. Don't wait till the end. If you want to interrupt, feel free to interrupt, so that we can keep it also interactive. Okay, so the very first topic I wanted to tell you is, another reason I really love to give this talk is, if there is a topic that comes to your mind, you want to work together, or there are things that we could collaborate with, we can talk about that, of course. So I wanted to give you an idea of what all we do in my group, so that some of the projects piques your interest. It would be lovely to talk about it further. So this one is data analytics and machine learning, where here we have, so this is a project that's been going on for the past two and a half years. Something that we started off thinking, oh, we can build these cool, magical predictive models, obviously was not that simple. We work with the Nemours DuPont Hospital for Children. The case study is sickle cell disease data set. So the idea here is to build predictive models to predict adverse risks in patients. In this case, they are children of almost under 12 years of age. So adverse events could be, a lung failure or a heart failure, or a stroke. So it could be, it's a binary classification. The prediction is if the child will walk through the door with an adverse event or not. So that's a prediction. And we predict this with genomic data set plus electronic health record. A genomic data set is only giving you details about the DNA, right? But the electronic health record will give you data about when you walk into when you go for your physical, all your data gets logged, right? And when you do this every year, you have all the data set as form of electronic health record, which is going to give you different types of data set than what a genomic data set would give you. So it's a mixture, genomic data set plus EHR. It's a heterogeneous data set. It is unbalanced. And this is sickle cell disease, for example, it's a rare type disease, which means you don't have 10,000 patients at a time. Nemours literally gave us 50 patients data set. And we know machine learning is a problematic thing when you have data set which is limited in size, right? So we have a small data set, it's unbalanced, it is heterogeneous, and there are association of features, which is what the third bullet is, complex association of features, because even to predict an adverse event, there is more than one feature which is associated with each other, which is another piece that you have to disentangle. And the heterogeneity. So all this made the subject, and the data set complicated. So classic machine learning data analytics models did not work because that is what we tested to begin with. This is some idea of what kind of data set we are dealing with. So it's 53 patients, 40 in control. When I say control and disease, control meaning they have sickle cell disease, but they have not walked in through the door with a stroke, as opposed to the 13 patients who belong to the disease cohort who are susceptible to the adverse event, which could be a stroke, right? So that's what the distinction is. But the point here is it is only 53 subjects, and it's a very small number when you have to apply machine learning classification on the data set, right? The last bullet talks about features. So basically, a lot of features in the sense, these are different arrangements of the DNA within your body, different concoction of, different types of, how do I put it? Different types of DNA sequences interacting with each other. And when there are tons of things that becomes a combination, eventually, which will decide if there is a stroke or not a stroke. So we're talking about 53 patients with 1 million features. Typically, the data set, if it's the other way around, machine learning classification becomes a tad bit easier. Say you had 1 million samples and 53 features, right? But this is a different kind of a problem. So the workflow that we have is my student gave a preliminary exam and he defended his, that's the first exam in the PhD cycle. He just gave this last month and he passed successfully, and we just submitted a paper on this. So, the workflow, what you see is basically you get the genomic data and the electronic health record data, there is noise. Sometimes when you get an Excel sheet from the hospital, there is a cell with no data. So you call it missing data, right? You can't just toss it off because who knows what that cell was, and who knows why it was missing. So there is noise in the data set, so you can't just toss off missing data. So you have to clean up the data, figure out where the missing data is, what is the population of missing data, et cetera, et cetera. And then there are different feature selection techniques because you want to see which features in the genome are actually causing the stroke. So among 1 million features, how do you select that handful of 5 to 10 features which are the cause for, a stroke? So that's the machine learning problem. And the workflow, the fourth column that you see, there is a rare allele enrichment, principal component analysis, SHAP values are 3 different feature selection techniques we try to use. It's not the end of it. There is many more you can do. And then classification, gradient boosting, you have a ton of these classification methods, right? But our goal is binary classification, prediction of an adverse event, yes or no. So there are different types of classification. In our case, just binary. So we need odd classifications, which is why we have in the voting, you will see 3 arrow marks coming out of it. So among the 3, which one you want to vote? So it's an odd number. Which classification almost accurately predicted that this patient will be susceptible to an adverse event. That's what you're classifying. The second flow graph, second picture that you see is of an existing AutoML tool called TPOT. And the confusion matrix is a metric that you use to classify patients, basically. And the reason to throw this here is to show that a traditional AutoML tool does not help with our case because TPOT did not classify the patients appropriately into the control and the disease cohort. For example, in the left-hand picture, you see 7 and 1, right? The control cohort and disease cohort. So among the 8 samples, 7 belonged to the one without a stroke, 1 in the disease cohort, which is still fine. But and the 8 samples were in the control cohort, so only 1 was mispredicted. In the case of the second column of the first picture, I don't know if I can move the mouse. Mouse doesn't show up. We see 4 and 2, right? So in 4 and 2, 6 samples were supposed to be in the disease cohort, but you only see 2, correct? So you see 4 in the control cohort, you see 2 in the disease cohort, when all the 6 should have been in the disease cohort cell. So this is what led us to believe that TPOT did not make the cut. TPOT did not help do the classification appropriately because it was using traditional ML classification techniques. So we landed up scrutinizing all the existing machine learning techniques and feature selection techniques, because apparently you cannot simply use whatever is out there. So we went back to the drawing board. Now we are trying to prepare the data, trying to figure out where things went wrong. And then we are not using an AutoML tool anymore, but we are building the top figure that you see, the entire workflow ourselves, which means trying a lot of combinations and permutations of which feature selection to use, which classification to use. This also blows up the problem, which is where the cool high performance computing comes into place, because now you have a lot of combinations to test, which we call hyperparameter optimization, HPO. And now you can use GPUs, you can use multi-nodes. We plan to use NVIDIA's Rapids platform, which will expeditedly run these different permutations, combinations on more than one GPU, when you can use Dask ML, multi-node plus Rapids, multi-GPU. So this became a massive problem, which NEMORs did not think it was, because they were like, oh, we're giving you 53 patients, can we classify? No, because it's tough, right? Because it's a machine learning problem. Anyhow, so this became a very important problem ever since we started going deeper and deeper and deeper into it, and we started figuring out, aha, so rare type diseases are a problem. Classic machine learning techniques are not going to work. Auto ML tools are not fit for this problem. So that's where we are. And my student, Mauricio, he's done a commendable job without any machine learning background, and he's dabbed into a lot of these different pieces in the entire workflow. And we are going back to the drawing board very often, which is what makes this problem very attractive, because we don't have a solution. So PhDs, you can't come with a solution to the blackboard, right? So you need a problem. So this is a problem. If it doesn't work, it's wonderful. If you feel like, oh my God, this is not working, I don't know what to do, that's perfect. Because that's when you need to find a solution, right? Because you need a problem. If anybody has any questions, feel free to ping me, else I will keep going to the next piece, which is the favorite topic of mine, programming models, and mainly focusing on on-node, because on-node lately are pretty heavy with, a ton of resources, multiple GPUs. So how do you tap into it? A classic question is, and the size of the boxes is not intentional. Just because I added to the boxes grew. So we have different ways to program, scientific applications. You all may have choices. Nothing is perfect. Nothing is the model. Anything that the scientific developer loves to use and solves the problem becomes the model of your choice, right? So there is just a handful. I'm sure I've missed quite a lot of them, but libraries, without them, none of this is going to work. Abstractions, programming abstractions at the language level is Cocos, Raja, directives, OpenACC, OpenMP, and I think the entire group is quite familiar with all these jargons, right? All of you are working on this format in some form or the other. And of course, we have the lower level frameworks, CUDA, OneAPI, all of those, OpenCL, etc. So I could pause and ask, what is your favorite programming model? But I don't want to take away the time. So maybe you could chat and tell me, which I could see before we shut off, what is your favorite programming model that you love to use? And I'll look at it as soon as we're, finished. Thank you.
Sounds good.
Okay. So again, this is something you all could relate to, a typical development cycle, analyze, because once you get a hold of a code, you don't immediately start parallelizing, right? You profile them, you study the code, you look at the sequential paths, you look at the parallel paths, then you parallelize, you don't like what you parallelized, you go back to the drawing board, you reprofile, right? So directives, my group uses directives a lot. But I keep telling them that if you are expecting 100x speed up just because you plugged in the pragma, it is not how it is. It is not magical, right? Because directives are very compiler driven, and compilers are not a magic tool. It's written by you and I. It's written by human beings, and we are not magicians. So we need, a little more analysis of every step along the way. So analysis, parallelize, optimize. You don't like it, go back, analysis, parallelize, optimize. And we keep doing this until we think that, okay, so there is nothing more to crunch, right? It's either an IO problem or it is, some overhead that if you cannot control, if you do not change the code entirely. So that's when probably you pause and you're like, maybe we're done. But I have some students that I just love them for this because they're like, no, we could do more. No, we could do more. I'm like, you have to publish, you have to get out of the door, you have to get a job, you have to leave, you know, at some point. So then we stop and we publish and the other person continues. You know what I mean, right? So, okay, so this one, I did want to tell you all about this one because it's kind of a massive project that's going on right now. So this is an exascale project where the goal is to prepare for the next generation hardware and software stack. And this is a project with Oak Ridge National Lab. And it's the project that the application is on Picon GPU. Do I see here, Nico?
My bad.
Okay.
Keep going. My bad, Sunita.
No worries. So, okay, Picon GPU. Picon GPU is a plasma physics code. And this is a CAR project, which means Center for Accelerated Application Readiness, where Oak Ridge hands out these projects every few years when they have a massive system being built, like Titan Summit. Next upcoming would be Frontier around the 2021-22 timeframe. In the US, there were 8 teams selected for preparing a code for Frontier exascale project. So my team is one of those teams where we work with HCDR, Michael Busman, Guido Yukeland, Alex Debut, who are the Picon GPU, Alpaca software abstraction teams. So this is, Picon GPU is a well-established code. It was a runner-up for ACM Gordon Bell Prize in 2013. So it's been running on Titan and Summit. The main challenge for this CAR project is more on the software level because the upcoming Frontier system is a different beast. It's AMD CPUs, AMD GPUs, and what worked on an NVIDIA GPU is not magically going to work on an AMD GPU. So that's where the programming challenges, rather let's call it opportunities, come in place. So there's tons of opportunities here. So that's what the project is about. How do you move Picon GPU that's been traditionally running on NVIDIA GPUs to AMD GPUs and the entire Frontier software stack, which is again significantly different to Summit. So we work with AMD very closely and Cray. And the most awesome part of this project is we get early access to baby Frontier, if you like, to bombard the system and give back and forth feedback to the software and hardware teams to prep the system for anybody else that will be using the system in the very near future. So it's a massive project with respect to collaboration and a lot of domain science input, which most of the times goes over my head. So we have to talk to the plasma physicists over and over and over again to understand their electron volt, to understand the laser beam. That's the Picon GPU that's we're talking about. The laser beam basically pierces through a matter, a structure. And when it pierces through, there are particles in the structure with opposite charges, which is what develops energy. So it's basically, imagine you are in the ocean and there is a boat going in front of you and there's, oh my God, I'm blanking out. There is this, what do you call that? The person who,
lifeguard?
The person who, tell me again?
Lifeguard?
No, this is not diving. It's the guy or the lady behind the boat that pierces through the water, right? What do you call that? There is a nice name to it, obviously. But
water ski. Water ski.
Thank you. Yes, water ski. Water ski. Yes, as simple as that, right? So when this person is piercing through the water, you see ripple effects. That's what I was trying to get to, right? So this is the Picon GPU is very similar to that. A laser is piercing through the structure. just like this person pierces through the water and creates lots of ripple effects. That ripple effects forms charges, which is what you need for energy. And along with the short of the Picon GPU, potential application is chemotherapy, for example. The sharper the laser beam is, the lesser healthy cells chemotherapy will affect, because we know there's a lot of side effects to chemotherapy, right? So why? Because besides the cancerous cells, healthy cells get affected because of the way the laser beam, is targeting the cells. So how can you have this high frequency, high energy, high voltage laser beam that makes sure healthy cells don't get affected? So this is the bio side of an application, but there is also matter and physics side of the application for Picon GPU. But this is what drives the reason to do the simulation faster, acceleration faster using Summit or Frontier in order to be able to simulate at a high electron, high voltage energy level. Okay. So number of challenges. So we use Alpaca. If you've heard of COCOS, right? So Alpaca is, the HCDR team will not like me if I say Alpaca is similar to COCOS, so I will not say that. But Alpaca is somewhere in between COCOS and OpenCL. Okay, so it is not high level, it is not low level, but the crux of it is Alpaca has many backends. So if you look at the offload column, you see OpenACC, OpenMP 4.5, SYCL, HIP, Silk Plus, CUDA, right? So it has several backends. So right now we are trying to create OpenMP 4.5 offloading backend for Alpaca to target Picon GPU on AMD CPUs and GPUs. We are also building a separate OpenMP 4.5 Picon GPU port so that we can directly use Picon GPU offloaded to AMD GPUs. Alpaca is to give that portability aspect so that you can target multiple platforms, because you do not want to rewrite your code for CPUs and GPUs. But that remains to be tested because you don't want to lose performance. So Alpaca is the top layer, and you have all the backends in the middle layer, and you have the target platform. And it's about 130, 150 lines of code with both Picon GPU as well as Alpaca. So this is not public yet, or I don't know if it is public yet. I just decided to show you folks. I've given this talk at the Open Power Workshop in November last year, but we have not talked about this to the card application review team. So I think it is not yet super public, but the goal here is figure of merit, where we have run the Picon GPU on entire Summit, which means all the nodes, all the GPUs, one full massive Picon GPU run. And you can see the number of GPUs it used, there's total particles per GPU. And the 14.7 tera updates is the metric Picon GPU uses. And you see the little dips, which is what we're trying to figure out with the Summit team. I think it is performance overhead, plus there are MPI calls, which is the reason why you see the dips. But approximately 15 terabytes is the form run, and it is supposed to be pretty good in a relatively speaking. And this is a big deal, and we have to achieve somewhere around these tera updates per second for Frontier. So this is kind of acting as a benchmark, basically. So in order to do this, as you can see, the level of how massive this is, obviously you cannot use Picon GPU directly because it's a big code for testing purposes. So we have Alpaca test codes, where we use to stress test any new compiler versions, new hardware architecture. AMD has their versions of hardware architectures before the main AMD GPU goes to Frontier. Earlier versions, we have the ones that we have access to, we keep testing them. And profilers, as you know, Summit is NVIDIA GPUs, so you would use NVProf or the new Nsight, but they're not going to work on AMD GPU, so what is a profiler? We don't know. It could be HPC toolkit, it could be something else, right? So that's another to do, which we have not tested yet. They have some preliminary tools going on, which we will be testing this week and next week. Then there is exposing and expressing parallelism at multiple levels, at the hardware level, software level, application level, and programming model. like I'm members of both OpenACC and OpenMP, and we know the politics side of it. But from my standpoint, with a neutral hat on, I keep asking both of them as to, okay, you have this feature, you have this feature. Can we get them to work together instead of recreating the wheel? Because it doesn't make sense, right? So with OpenMP 4.5 offload, there are some features which are problematic. Those features have been solved with OpenACC. So can you both talk to each other and figure this out? The short answer is no. But with this application, you can make that happen, because it's a very clear case study where some features work, some features don't, some features are implemented, some features are not implemented. So what do you study from the other features? We're also leveraging Alpaca, which is for portability, C++ abstraction. And I like Alpaca because the parallelism is within the language. Now, directives may not exist 10 years from now, and this is my personal opinion. There are some, there are issues with using directives, and every time a new parallel pattern comes to play, there is the high-level programming abstraction does not quite work. So you'll end up going to design the algorithm, prototype, and create a new abstraction, which is how the OpenMP tasking has blown out of proportion, because you have a lot of tasking features now. Having said that, if you're able to embed parallelism within the language, then, from the scientific developer standpoint, they don't need to learn Alpaca or Cocos or OpenMP or OpenACC, because they know C++ Fortran. So how about expressing parallelism at the language level? The language, specification folks argue that, oh, we cannot use just C++ to express all sorts of parallelism, which is why you have, OpenCL, OpenMP, OpenACC, Cocos, and Alpaca. So there's more than a thin line, but the goal should be that people don't recreate the wheel, because we have enough problems to solve. So the goal with Car Picon GPU is HIP, which is the backend for AMD, ROCm, all those are backend for AMD GPUs or AMD software stack. Then HIP backend, OpenMP offloading, and then this is work very close in collaboration with the OpenMP offloading compilers. As you can see, there is a laundry list of compilers, and not all features work in all implementations. So you need to do testing of which features actually works and stuff. So creating tickets, issues with new feature requests and programming models. How are we doing with time, Hatim?
So 30 minutes, half an hour right now. So you still have, 20, 25.
Okay, so maybe I'll take another 10 to 12 minutes, tell you about another case study. Meanwhile, I'll probably take a sneak peek at the chat to see if there is any public demand for solar physics or biophysics. Aha, of course.
Yeah, in the audience, you have many computational scientists from our supercomputing lab. And they will be very interested in listening to those scientific applications that you brought in to various hardware architecture.
Okay. So maybe I can tell you both. One is published, so obviously you can get more idea from reading the paper online, but I don't want to give you a crux of it. The other one is another interesting problem, which we are banging our head against the wall to see where the bug is. So I want to tell you about that a little bit so that we don't repeat the problem, right? So what not to do, more like it than what to do. So this is the other side topic that I wanted to let you folks know. Again, this is not public yet. So I guess several of you would have heard of Spec HPG, right? There's a Standard Performance Evaluation Corporation High Performance Group. So we are working with, so there's a bunch of universities and industries and labs across the globe where we are working on a suite called HPC 2021. It was 2020, but we couldn't make it, so it will be 2021, where the idea is to take representative benchmarks of scientific applications and put a suite together. So the suite spans weather modeling, different types of physics problem. Picon GPU is one of the code. Another code from my group is Minisweep, which is a radiation transport code. Then there is T-Leaf, Chloraleaf from Simon McIntosh's group, so on and so forth. So there are about 15 to 16 applications. We recently did a benchmark selection. I shouldn't say much because there's going to be a press release and, et cetera, et cetera. But the bottom line here is we decided to create a suite which represents scientific applications. Some of them are mini applications with different workload sizes. The whole goal is to be able to stress test hardware and software of large-scale supercomputers. So beyond LINPACK and HPCG, which are two very important benchmark suites that the supercomputers currently use, what if you had an additional benchmark suite that actually represents application kernels, and you ranked the computers accordingly? So that's the motivation behind. With spec harness, you're able to add a bit more of infrastructure to it, robustness, accuracy testing, different workload sizes, and there is a structure to the entire suite. And we have 5 steps, and we have been working on this for the past 2.5 years, where every code has to pass certain tests and certain steps before the team votes the application into the suite. My own one of the application got dropped because we couldn't port it to more than one programming model within the time cutoff. So the goal is to also keep 4 programming models. So OpenMP, offloading, OpenACC, MPI. Hatim, this is not public news, so no Twitter. So just letting you know.
Sure.
This will be a supercomputing thing, but I know your group, and I wanted to tell you because you guys have this supercomputer, that you would probably want to test it with the suite when it is released.
Sounds good.
Every individual application developer can do his or her performance modeling on their own application. So spec wouldn't do performance modeling on the application, but mini Castro, for example. So the Castro people would do performance modeling. Then you could do weak scaling, strong scaling on every application. Some real applications do very poorly with strong scaling, and some developers do not want to show strong scaling. Sometimes they want to show only weak scaling for application reasons. So it's a kind of a comprehensive suite, and we wanted it to be as thorough as possible, which is why we won't be releasing all of it in November, but I think there's a teaser trailer coming up in November if the plan, everything holds still good, and I hope you folks can make the best use of it. Okay, so this is intro to a programming model for the case studies. I believe all of you would have heard this by now. It's OpenACC is one of the programming models, like OpenMP. And the latest version as of this week, and I should have updated the slide, is 20.7. So the last bullet will be, if you get the NVIDIA SDK, the entire tool, I think PGCC is called NVC, you get 20.7, and it is licensed but free to use because we just downloaded on our systems just about yesterday, and we know it works. And you get Nsight compute, tools and everything with the SDK suite. Okay, so yes, I'll tell you about both the problems, but I'll be quick. One is the biophysics problem, and this is my poster child project because it started off with 2 undergrad students as an undergrad research project, Eric and Mauricio, and after 2 years of working on the project, they came to my office and they were like, "Oh, could we do a PhD with you?" I'm like, "Oh, sure," because they know me, I know them, and the interest that intrigued them to do the PhD because of this application, what makes this project really wonderful. And I had my student Robbie, who graduated last year, and he is now with NVIDIA working from Oak Ridge for Summit, and Alex from chemistry, so which is what makes this even nice because it is an interdisciplinary project. It's not CS only, but Juan Perea from Department of Chemistry, Biochemistry, UD, and us. So the crux of the problem is, does it revolve? See, perks of working with application scientists. You get cool GIFs, you get cool animations, because computer scientists can give you plots. We can't give you this. So I really like to show this, so thanks to Juan Perea and his team, this did not come from my group, for visualization of an HIV capsid. So this is an HIV capsid, and what you saw in the previous slide, the 2 pictures that you see, my students got overexcited and they 3D printed an HIV capsule. This was for a poster competition. So again, the reason was all other kids were showing robotics, drones, and physics and chemistry experiments, and we had nothing. We had plots. And JP Morgan Chase were the one that were judging our posters, and they don't know computer science or physics or chemistry. They are going to go with what looks cool, right? So they were like, okay, we have to do something cool. So we landed up printing HIV capsids, and we kept it on our table so everybody could touch and feel it. Obviously, everybody loved it. But so that's the crux of this summary of this problem is it's we got a serial code from Ohio State University, X lines of code, doesn't matter. It's a decent sized code, which basically predicts the chemical shift of protein structures in our human body. And we need to know which direction the chemical structures go, and it is important, especially for vaccination, drug discovery, and treatments and all those things. The serial code from Ohio State is also a function that is apparently used in GROMACS kind of application, the massive molecular dynamics application, AMBER, GROMACS kind of applications. So the serial code ran for 15 hours. That's where we started. And 2 undergrad with no background with parallel computing or architecture. So starting training from ground up. So it took about a semester to train them on tools, get them access to local clusters, right from SSH. They started from there, right? NVProf and everything. So serial profiling, and the takeaway here is when you look at a scientific code which has not been parallelized, you want to see which portions of the serial code that you can clean up. When you clean up the code, you are already solving half the problem. At least that was the case with this problem. You see the 23% get select pi, right, in the entire pi. Although when you look at it, you are seeing 35% get contact is the biggest pi there. So that's the one that needs to be accelerated. Instead, we saw a lot of funky stuff going on in the 23% get select, which was just a serial portion. So we decided to look closer and clean it up, which means, functions or codes that were called within a for loop X number of times when they could be hoisted outside the for loop, and you don't need to call the function 10,000 times. As simple cleaning as that. So when we just did that, if you see the right-hand side plot, 23% vanished, right? So it went away because it got all cleaned up, and we see the next big portion there is get contact, which everything gets shifted, which is why the development cycle is analyze, parallelize, optimize, analyze again. 44% get contact, which is the one that we wanted to accelerate further. And we used OpenACC. OpenACC gives you 3 levels of parallelism: gang, worker, and vector, which helps with the grid streaming streaming processors and streaming multiprocessors in the GPU architecture. So little green cores that you see in the GPU, and the big box that you see with so many different cores. So 3 levels can be addressed with the 3 levels of parallelism in the programming model. So that is what we basically did here, applied gang and vector, 2 levels of parallelism on the top, and parallelized the code with OpenACC pragmas. And what you see was 14 hours estimate, serial, unoptimized, cleaning it. Look at the number of seconds, right? 2,614. So it drastically brought the code, time taken down just by cleaning the code. And then multi-core, and then we applied a Pascal 40 and a Volta 100. And eventually you see 47 seconds. So 14 hours to 47 seconds, if you compare serial to Volta 100, and 146 seconds, approximately 2.5 minutes or so, to 47 seconds when you compare multi-core and GPUs. And this is an undergraduate project. By the time we finished up, we wrote it when the students were in their PhD program. So it's about 2.5 years of work. An experienced programmer would get this done in 6 months. But this is what it is, right? You train the next generation workforce to get them to where they are, and it takes time. And I would say this was not a complicated project. This was actually a simpler project because the parallelism is staring at you, and you use the profiler tools and you manage them. But the students weren't aware of how to even do it. So you train them from ground up, and we were able to publish this in PLOS Computational Biology just about 2 months ago. Then it also won the Best Poster Award in ISC last year in the HPC category. So students were very happy, and then we printed 3D molecules, so they can't be happier. And now they are pursuing PhD on 2 different topics. So yeah, I'll let you read more about that in the paper. The other case study is solar physics project. This was one of the students who worked on the biophysics project. So now we work with NCAR, National Center for Atmospheric Research. If you have heard of NOAA, weather prediction, NCAR is a similar organization like NOAA, MPS, which is in Germany. So I'll get to the main issue of this code in a minute. The motivation of this code is NSF has funded for a multi-million-dollar telescope, which is sitting in Hawaii, gathering data from the sun. So we are basically studying about the sun. So expediting simulations of the sun, because we are getting data in a capacity more than we can ever manage from the telescope. So you have big data problem, but you are still processing in a snail space. So you want to accelerate the whole simulation so that you can get all the data from the telescope. So here the issue was, and this is not what we should do. We did not put regression testing in place on day 1, which was the main problem. We had the serial version of the code, we parallelized it, we accelerated accuracy issue, and you cannot have accuracy issues with codes like this, right? So the parallelism threw off the accuracy, and we hit okay, this slide tells you the different tools you can use. NVProf, CUPT, CUDA occupancy calculator is a beautiful, beautiful Excel sheet. If you work on GPUs, I would definitely strongly recommend you to look at the occupancy calculator, which gives you tons of information about the GPU, like register pressure, and register pressure is a massive problem, and occupancy of shared memory, global memory, all sorts of data. And PCAST is a tool from PGI OpenACC, which helps you look for correctness between a CPU code and a GPU code, which is what told us that there is an accuracy issue. But guess what? The PCAST tool had a bug, which is what this code found out. And then we figured that PCAST tool itself has a bug, and we resorted to Jupyter notebooks and regression testing at the end of it. Some numbers of the different functions in the code, of which stands on the top. NCAR is very much interested in the radiation transport, RT code, and magnetohydrodynamics, MHD, which are 2 important pieces that they often see in their MPAS kind of, weather codes and solar physics code. So that's it's in seconds, and the profiler basically. These are again some NVProf output to show the gold and the blue bars, where the gold is your computation and the blue bar is a lot of data movement. Memory copies, host to device, device to host. You do not want a ton of host to device, device to host copies, because that's going to derail your performance. So you want to overlap computation and communication, which means your gold bar and your blue bar, they better overlap, right? So this was evidently a problem, and we had to make sure we were looking at performances here. And this is the algorithm of the problem itself, where you're looking at a 3D cube and you have slices of different colors. So you can parallelize within a slice, but the slices have to be parallelized in a predetermined order, which is where somewhere the code had an issue. And you see the different colors in the NVProf output are the different slices of the 3D cut problems, and it's a radiation transport code. This is a different type of radiation transport code, and I say this because in the other radiation transport mini sweep kind of a code, typically the neutrons are flowing from one end of the cube to the other end of the cube inside your 3D picture. They are not colliding, they are not converging, they are just flowing from one end to the other. So here it was 20 to 30K lines of code, Valgrind, GDB, all possible debuggers, Python notebooks, PCAST, PGI tool, different test beds, GitHub. But we ran across a problem in December, and we couldn't submit to pass of 2020 because we had this tiny little bug in the parallel code, which we had no clue where it was emerging from. Why? Because we did not have an appropriate testing in place. We just kept parallelizing, which is a bad idea to do. We kind of I think we know where the bug is, so we are going back to step one. So we kind of rewinded to the very first GitHub commit, and every GitHub commit is being done regression testing at the moment. So these are the Jupyter Notebooks regression testing output. On the right-hand side plot, you see a little blurb, red dots, right? So that is the error, and that red thing has to go away. So the left-hand most plot is the ground truth. The middle plot is what is out of our code, and the right-hand side is the difference, the most right-hand side. So that little red globs should not be there. So which is a flux problem, which is, I think, an error about 10 power minus 3 and above. And I think we have nailed it with the regression testing, but it took us forever because we did not create a proper structure to the code. So please don't do it. If you're working on a massive scientific application, you want the regression testing in place. You want to test every commit to the system, because we have my group, we have NCAR, we have Max Planck. So 3 people, 3 into 2, almost 6 to 7 people are working on a code base. So we all commit, right? So who's doing the testing? Nobody was. So then we paused in February and March. We wrote a lot of testing code, Jupyter Notebooks, which is a result of this. And that kind of nailed down the problem. I wish we did this in 2018. By now we would have had a paper about this, but we don't. So let's not do that. Some experimental setup. Yeah, wait, I think I should jump on to the training and education piece so that you know this exists. So you might have heard about this, right? I think Saber and some folks do hackathons, boot camps and things, or you're, I'm pretty sure, aware of this. So this is from the gpuhackathons.org, which has a list of different events going on across the globe. They constantly look for mentors. Also, if you have PhD students, which you do, and you want them to have some hands-on training, I sometimes just send my PhD student to work to shadow a group. So observe from the side, even if you cannot contribute, but learn. They're also doing a wonderful job with virtual hackathons these days. They have already conducted 3 to 4 virtual hackathons, and my students have been participating as mentors. And they were team members in the very beginning, and now they have graduated to be mentors. So it was not 2 days job. It took 2-3 years for them to be mentors right now. But yeah, there are several events, and that's just the crux of the events going on across the globe. If you want to participate in any capacity, I'm very happy to introduce you to the organizers who are constantly looking for people to help them with the code. So these are scientific applications with 4 to 5 members, 2 mentors per code, and usually just 5-day hackathon in person, but now they have spread it out across 2 weeks so that you're not sitting in front of Zoom for 8 hours. Yes, so that's my group. The current scenario, current situation in life, all of us online. And trying to keep this up, every week almost, because they were like, oh, we could meet online every week. I'm like, sure, let's do that. So we have somehow continued our Zoom meetings just like you folks are doing, and what you have done is such a wonderful idea that I will probably do the same and invite you folks to talk to my group, just to keep them motivated, right? So these days, motivation is a very important factor, and you can quickly go down in the motivation curve if you don't have fun stuff going on. That's me, finally. So, feel free to contact me at any point, and happy to take any questions.
Great. Thank you so much, Sunita.
Yes.
Let us send you an applause. Right. Great. So let's see. We have a question from the audience, or comment, or anything to Sunita.
Thank you, Sunita, for joining our group. And yeah, we should we should get to know your group better. I see a lot of you at all the the committee meetings for all the international conferences, and we greatly appreciate the work that you do, not just scientifically, but in terms of promoting high performance computing professionally. So thanks a lot.
Absolutely.
For those who don't know, probably everybody in this hearing knows, because I made sure you were all very well informed about ISC 2020, which we had in June. But Sunita is the track lead for one of the curated tracks on programming models and performance models. So we went straight to the top here.
Oh, it was fun. It was the amount of Twitter traffic ISC led. It almost felt like we were there in the convention center.
That's good.
Almost there.
Sunita, I have a question for you. So in the slide where you talk about Alpaca, you showed you went from 80,000 lines of code to 50,000 lines of code. Is this a move to C++ advanced feature? How can you explain this? Reduction in terms of lines of code. I'm just curious.
Yeah. So before it was, I think this was more on the C++ abstraction features.
Okay.
Trying to wrap things into functions, this is the work. Alpaca is from HCDR team. So the code was already written in Alpaca before, the car project even started. But definitely Picon GPU was, the parallelism in Picon GPU expressed via C++ language level abstractions is what crunched the number of lines of code down way much. I would also take this with a pinch of salt, because if you look at Alpaca's, say, matrix multiplication code, it is 500 lines of code.
Sure.
So it really blows up, when you can write a simple C++ or an OpenMP, OpenACC matrix multiplication. So it really depends on the kind of function you are tackling, I would say. And it's not super straightforward, but when you can express parallelism at the language level, you can tie some things up within the abstractions itself.
Great. All right, I have let's see, Bilal.
Hello, good morning or good afternoon. Good morning, Sunita. Thank you very much for this nice presentation. I have two questions. One is about the when you shared about the regression testing. So you shared about the IBM XLC. So will it be still like ongoing effort, even though it will not be part of the future Coral machine?
Excellent question. So I'm glad you asked, because that's a piece I couldn't talk about because running out of time. So this is the OpenMP offloading validation test suite project. It's an exascale project called Solve. The website on the top, if you click onto that, CRPL is my group's name, OMP VV Solve results, you will get all the results of all the compilers that have currently implemented OpenMP offloading, including Excel. So this is a summit-based project, right? So I would imagine Excel compiler, I know the project is until 2022 at the very least. So until then, at the least, we should be testing Excel, because the funding is from Oak Ridge. And until Summit is, I think, deprecated, we would continue to do the testing. After that, because this question has come up within our OpenMP validation suite project, we are trying to work with OpenMP team to keep this going, because after Solve, after funding, right? I have a master's student, undergraduate student working on the project, and they are being funded. So when the funding stops, what happens to the project? Classic problem. So we are trying to work with the OpenMP team, who are obviously vested in each of the offloading compilers, right? To see if somehow we can work together to keep the testing going in terms of nightly tests. Even if Alex Bate, for example, even if somebody like that just tests the suite nightly build and sends us the results, that's step one, right? So we are hoping that the project doesn't die, because I know AMD, GCC, Clang, there are some point people who invest, and I believe they would still do the testing irrespective of ECP, Summit, Solve, what have you. So, and I plan to somehow keep it going with incoming students who will probably learn from this project, you know, and maybe I have some little funding for them to keep this going. But this validation test suite is an awesome way to learn about a model, because you're writing a very small unit test case per feature. So you know the in and out of the feature by writing a test case. So, you know, so yeah, the long and the short answer is I hope we will keep continuing to test, because I think if Summit is not there, there's a new system, it's not end of the world, right? Because there are just many more systems, and different systems use different compilers.
Especially like when you see like, for example, here you evoke like a Clang, that would be great, especially like now, even with the Cray compiler, like for the C, now they're adopting the Clang, but for Fortran, they see that the main Fortran from Cray is still like strong, so they would like to keep it. And I think like it will be a great opportunity also for you, like to see if there is an opportunity like to them to, I know like they stopped kind of going with OpenACC, but they still keep the Open MP going on, which is very important.
In this, we don't see Cray yet, but Cray compiler is the other one that we have to test. You know, we haven't tested. This is really giving deliverables to Oak Ridge, because the other one's paying us. But we get asked by Intel, where is Intel on the chart, right? So those are the side stuff that we have not done, because we're just so busy giving Oak Ridge deliverables. But at some point, got to pause and just test from a project standpoint, which is where we are trying to seek help from OpenMP. But OpenMP is a huge group of members at the moment, right? So it's a lot of convincing needed. When you have a big group, there is a lot of discussion, and maybe sometimes there is never an ending.
Thank you very much. And the second question was about the regression testing. So it's one of my favorite, like working theme, like in my side, but more towards the hardware, especially like for the change and for the upgrade. And so for you, like what I like it seems like you do both for the hardware and also software. And I look forward for the SC20 announcement with the spec, like new feature. So what have you seen like typical error on what you shared, any bugs? So is it related more about software or also hardware?
With the spec, it has been software mostly, because different type compilers, you know, libraries, tools, and because of spec, the compiler vendors update their versions, release new versions, we'll end up testing them. Having said that, there are some codes that give us hardware errors, and we reach out to the scientific developer to help fix, because it's just beyond our expertise from the spec hat standpoint. But those hardware errors have not been captured as part of spec results for no particular reason, you know. So it's more on the software side, I would say. Like the ECC bugs, you know, sometimes when you come across that, we obviously ping the hardware vendors and we try to work with them, but the vendors work with the science developers. So we step out of it.
Excellent. All right. We have a question from Rabeb.
Oh, yeah.
Yeah. Hi, Sunita. How are you?
Very good. How are you? Good to see you here.
Congratulations for your last teaching award. Actually, like Twitter was filled with a lot of congratulations for this outstanding achievement.
Thank you very much.
Yeah. I have actually a question regarding Alpaca. Alpaca, I first heard about it in your talk, I think in Power Open series talk. Like I can see the difference between Alpaca and Cocos, but I don't know where's like Alpaca located compared to Raja, because I can see similar objective in like in Alpaca and Raja right now.
So I have not used Raja, so I don't know how to quite compare. Alpaca, to me, looks closer to OpenCL. And the Alpaca group, HCDR, may correct me here. So I don't think I would, don't quote me on this, but it's closer to OpenCL because it's got a ton of, low-level abstractions. And initially, I thought it was closer to the CC++ objects, classes, polymorphism, those kind of things. But it's more closer to the OpenCL, which exposes the GPU hardware, yet kind of wraps it up within the abstraction than you trying to really write a CUDA level code, if you like. But going back to your question, I have not used Raja, so I don't know. But I will follow up with you because the Alpaca team may have, when they did, performance evaluation between Cocos, Raja, and Alpaca, because this comes up, when we talk about this in meetings, mostly between Cocos and Alpaca. But I'll get you an answer.
And I can see recently, like in the HCP report, that they are trying to merge Raja and Cocos in one software layer.
Mm-hmm. Mm-hmm. Yeah, I see that too. Yeah. I think Cocos, in my opinion, used more, probably because they do more tutorials, more outreach, and more applications been using them. OpenACC is working with Cocos in a broad stroke to try and see what within the language can be expressed in parallelism, and OpenACC can, deprecate the feature once it is exposed in CC++. But we haven't quite worked with Raja for no particular reason. I think Cocos is more widely available and for use just because out of the tutorials.
Yeah. Thank you.
Yeah. I'll follow up with you on the Raja question.
Right. Any other question?
Hi, Sunita. This is Long. Thanks for the talk. I have just one more question on the support of OpenACC for the GCC compiler. Is things get done now with the support on both NVIDIA and the AMD GPUs?
Thank you for asking that. Mentor Graphics has an AMD port or AMD support for AMD GPU on OpenACC. We recently wrote a blog. Mentor Graphics wrote a blog on OpenACC website. So I will send it to you because there is a link to it which has specifically versions of OpenACC within GCC that you will need to target an AMD GPU. Cool. Yeah, it's work in progress. And this is, again, a question that is very often asked. So we asked Mentor Graphics to clarify, what works, what doesn't, because if you simply download a GNU compiler, you won't have the OpenACC branch. You have to download it separately and link it. And there are different versions which supports certain features and certain features it doesn't support. But yes, there is a working version from AMD GCN device.
Okay, thanks.
Mm-hmm.
All right, any other question? I guess I have the last one. You had a strong statement, Sunita, which is, you had many of those, but one of them is, the idea of expressing the parallelism at the language level, right? So Cocos, for instance, and other similar, packages. So, what about, what about support from not only the language, but the programming tools and programming models for mixed precision computation? So are there, are you familiar with any, perhaps, or maybe you have some insight in, the programming tools and models to support inherently, perhaps the detection within a given application where you could perhaps, swap to lower precision computation without really sacrificing the ultimate accuracy that you are after. Are you familiar with some automatic approaches to detect some, section where low precision computation can really bring performance? The compiler is an X-ray, right? So as soon as you compile your code, perhaps there are a few things that compiler can do. And do you have any insight on this, or maybe idea on how this could be? I mean, this hot topic of mixed precision could be supported moving forward in the compiler community and programming model.
Thank you for asking. It's a good question. It's a very good question. I do remember my group doesn't work on this particular problem, but among the papers that I review, I should check if the ones that I'm referring to got published or rejected or whatever, so I won't give too many details here. But there was a Clang-based compiler work that had come up with optimizations to trigger that lower precision optimization. And that set of authors had also compared it against GCC. So let me look up, this particular idea. There was also a machine learning work that, again, it was one of the paper reviews I did, I forget which one, where machine learning was used for like a bunch of permutation combinations of compiler optimizations data to come up with the classification models, but for compiler data. So imagine you have data from the assembly level, and a lot of these data at the assembly level, but you're using classification methods to see which of those are applicable for lower precision. And I can say that this GCC did poorly in that paper. Clang did better in terms of classification. And this was also, there's a thesis on this, and that person I can put you in touch with. He defended just last week, where he used the Russians algorithm to sparse matrices to find out lower precision optimization for different systems. So yeah, this is how far I know. So not sure if it's useful, but
sure. Great. All right. Well, thanks again, Sunita, for joining us today on a Sunday early morning at your place. And we're very happy to have you with us. And well, I mean, let's thank Sunita again. And I guess
thank you, everybody. This is wonderful.